Covariance and correlation. Covariance measures the degree of co-movement between two variables, in this case x and y. Now there's two kinds of data sets for which we may calculate covariance. The first one is using historical data, and the other one is forecasted values. So let's see what the difference is between the two sets of data. With historical data, all the observations have already occurred. Therefore, each observation gets the same weight. So if there's 20 observations in the historical data set, each one gets a weight of 1 over n, or 1 over 20. Now, how do we actually measure the degree of co-movement or covariance? Well, we like to see what x and y were doing relative to their averages at the same time. So for example, if x is above its average, this would be positive. And if y was above its average at the same time, then both would be positive, and therefore positive times positive would be equal to positive. At the same time, if every time x is below its average and y is below its average at the same time, then both factors would be negative as well, but then negative times negative would also equal to positive. So what does a positive covariance tell us? It tells us that x and y always move in the same direction, or generally move in the same direction. So if x is going up, in other words, if x is above its average, y is above its average. At the same time, if x is below its average, then y is below its average. So in both those scenarios, x and y are moving in the same direction, and therefore covariance will again be positive. Now, to actually work this figure out, what we have to do is we have to make a number of observations. So we sum them up. So remember, this represents just one observation. So if we have a large data set, we have to measure what x and y were doing its relative to their averages for all those points of observation. And then, as we said before, each one would be assigned a weight of 1 over n. And that's really it. So this is how we quantify covariance. Now, how about if we're looking at sample data? So again, we're under the historical data set, but now we're just looking at a sample of the historical data. The only thing that would be different if you're using a sample as opposed to population is that the degree of freedom would be n minus 1 as opposed to n. So for a population where the weight is 1 over n, if it's a sample, the weight of each sample observation would be 1 over n minus 1. Well, what if we're looking at forecasted values? Well, now with forecasted values, these values haven't occurred yet. So the only thing we could do is assign probabilities to them. So the only thing that's going to differ between historical data and forecasted values is what kind of weights we assign to these observations. As I said before, with historical observations, all the data points have occurred, so they get the same weight. But with forecasted values, they haven't occurred yet. So the weight that we assign to each potential value is equal to the probability of its occurrence. And that's the only change we're going to make. So we're going to substitute the 1 over n, which we used here, with the probability of that forecasted value occurring, which is right there. And you can see the transformation right there, ladies and gentlemen, right there. That's the only difference between the two approaches to calculating covariance. So rather than having to grapple with two different frameworks, it's really just one framework, with the only difference being how we calculate the weights. Now, to put the covariance into perspective, we scale it relative to the volatility of the underlying pair of assets. And the result will be correlation. Now, correlation can be abbreviated using either this symbol or this symbol, so we'll use them interchangeably. And this just tells us what the correlation is between x and y. So as we said before, what correlation does is it takes this degree of co-movement and says, okay, how big is this co-movement relative to the volatility of the two variables that you're looking at? So when you scale this co-movement, you get a parameter or a range. The lowest value that correlation could take on is -1, and the highest value that correlation could take on is +1. So it'll be within that range. Now let's interpret possible correlation values. So if correlation is +1, that would indicate that X and Y are always moving in the same direction. So the always is represented by the fact that the correlation is close to 1, and the same direction is represented by the plus sign. Remember, when covariance or correlation is positive, that means they're moving in the same direction. But the only question is, how often are they moving in the same direction? Are they moving in the same direction some of the times, most of the times, or in this case, all of the times? Let's look at the other extreme. What if the correlation was -1? Well, let's break it down into pieces. So 1 means that it's a very strong relationship. There's a very, very strong relationship. And the negative means that they're moving in opposite directions. So when you put the two together, the conclusion is that X and Y are always moving in opposite direction. And then, of course, you can have all kinds of possible values in between. Let's just look at one other critical correlation value, which is 0. When you have 0 correlation, remember how you get 0. So if this is 0, you got to remember standard deviation is always positive for risky assets. So the only way correlation can be 0 is if there's absolutely no co-movement between X and Y. So the conclusion, if correlation is 0, would be that X and Y have no relationship with each other. So let's summarize here. As I demonstrated before, correlation reveals two pieces of information. The direction of the co-movement, so are they moving in the same direction or in opposite directions? But at the same time, correlation reveals the strength of the co-movement. So if it's close to absolute 1, so whether it's +1 or -1, doesn't matter. If the numeric value of correlation is close to absolute 1, it means there's a very strong relationship. I mean, look at it. The word always, right? That means there's this pretty strong relationship. And if it's close to 0, so if the correlation value is close to 0, it would mean that there's very little relationship or co-movement between X and Y. And that's what we demonstrated right here. Now, correlation can be illustrated using scatter plots. And what scatter plots is as follows, ladies and gentlemen. It's just data points representing observations of X and Y. So let's look at case A. So let's just pick this dot and interpret it. This dot represents, so if we're looking at stock returns, so if these are two different stocks, this point right here represents what the stock return was at the same time for X. Sorry, that would be, this would be the return for X. So let's just say this is representing an observation for monthly return for January 2021. So then in January 2021, X had a return here, whereas Y had a return there. So do you see how each dot represents a simultaneous observation of X and Y? So of course we plot a whole bunch of data series, and then we try to see what the relationship is between X and Y. Now in this case, you can see that every time X goes up, Y goes up. Similarly, going from this point to that point, you can see as X goes up, Y goes up. And similarly, you could see me illustrating here as well. So there, X and Y are always moving in the same direction. As a result, the correlation here would be +1. How about in scenario B? Let's see what's happening. And again, remember that this is X. So if X, when X goes up, Y seems to be going down, right? And even here. So when Y goes down, X goes up. So therefore, they're always moving in the opposite direction. And as a result, correlation is -1. So what's the first immediate observation you make? You can spot correlation just from the slope of the curve. So if we drew a curve here representing each of these observations, you can see that the slope here is positive, and therefore the correlation is positive. And similarly here, the slope is negative because it's downward sloping, so correlation is going to be negative. So that's a good way to determine if the correlation is positive or negative. Now in the case of case C, you can see that there's no relation between x and y. So for example, let's go from here to there. You can see as x goes up here, y goes up here. But then in the second scenario, going from here to there, as x goes up, y comes down. So there isn't a consistent relationship between x and y. So therefore the correlation would be 0. And again, a good way to spot what the algebraic sign of the correlation is just by looking at the slope right there. And it's a flat line, so giving you an indication that correlation is 0. Now case D is very interesting. Case D is very interesting. If you drew a line of best fit through the data, so if you drew a line that cuts through the data, you could see that it would be right here. So if you drew a linear line, that's the catch. If you drew a linear line between the data, you could see that it would be a flat line, and therefore it would tell you that correlation is 0, right? However, if you take a closer look, on the left side of the scatter plot, you can see that the correlation is downward sloping, so it's negative. But then if you look at the right side of the scatter plot, you could see that the correlation is positive. It's just that when you combine the entire data set, that the correlation seems negative. So therefore, this is a segue into the limitations of correlation because, ladies and gentlemen, even though, like, if you entered this data into your statistical software, the outcome would be correlation of equal to 0. In other words, your software would indicate that there's no relation. But when you look at the scatter plot, there is clearly a pattern happening here. There's something going on. So why is it that correlation wasn't able to capture that pattern? Well, correlation only measures linear relationship between x and y. So as we saw in case D, there's clearly a strong relationship between x and y, but because that relation is not linear, correlation did not capture it. Instead, it told us that correlation is 0. So this is definitely not a linear relationship, right? And correlation says, well, if there isn't a sort of a relationship or a linear relationship, then the conclusion is that this is 0. The other limitation of correlation is the impact that outlier or extreme values will have. So in the first case, let's just look at the observations A, B, C, and D. And you can see that if you draw a line, a linear line that fits through A, B, C, and D, you can see that all 4 observations are tightly around that linear line, indicating that, you know what, there's a pretty strong relationship between x and y. And it's right there. So without observing that guy. But then when you include observation E, now observation E is regarded as an outlier, and you can see why it's called an outlier. Because here's the original 4 observations, which is, tightly centered around that line of best fit. And then you've got this one value that's way out there, right? But if you include observation E as one of your data points, and then you draw a line of best fit, so if you wanted to construct a line that cuts through A, B, C, D, and E, then this line right here would be the line of best fit. But then you could see that that line is flat. And remember what we said, you can spot the algebraic sign of correlation through the slope of the line of best fit. And if you just have a horizontal line, it means y is not sensitive at all to what's happening to x. You could see why. Whether x is increasing or x is decreasing, the value of y is just remaining stationary. So there it is. With the outlier, now correlation is close to 0. So therefore, judgment is required as to whether to include or exclude outliers when calculating correlation. And that's what distinguishes a good analyst, is judgment and discretion. So it's up to you to determine whether E should be included in the analysis or not. So generally, if you think E will occur more often than not, then you would include it. But if you think event E was just a one-off event, very unlikely to be repeated in the future, then you would exclude it, and you would just calculate correlation using these 4 data points. The third limitation is spurious correlation. So even if the correlation is strong, i.e. close to an absolute value of 1, it does not necessarily mean there's a true relationship between X and Y. Instead, the sample correlation may be strong due to the following factors. So first of all, it could simply be to chance or coincidence. So for example, if you mine a data set enough times, you may find some coincidental relationships. So for example, very long time ago, someone noticed a pattern between which football team won the championship and how the stock market performed that year. Yeah, but that's just a coincidence. Like if you look back at thousands and thousands of pieces of variables and their data points, just by the sheer law of numbers, you're bound to find 2 variables that exhibit a high correlation with each other during that time. But again, that's just a coincidence, because you were just mining the data, right? You were just sort of looking blindly to find the relationship between any 2 variables. So here's the question I have for you. Remember that example I gave you about based on which football team won the championship, the stock market either outperformed or underperformed. Would you ever use that as the basis to manage your own clients' portfolios? Absolutely not. What's the other limitation? X and Y may both be related to a third factor rather than having a direct relationship with each other. So for example, if the market had a very strong year, then chances are most of the stocks listed on the market would have had a really good year as well. So we're assuming that if the market had a good year, the stock return for X and Y had a really good year as well. But does that mean X and Y are related to each other? Or is it because they're both linked into the market? So it would be faulty to say there's a strong correlation between X and Y, because the true correlation is between each individual stock and the market.